A recurrent neural network is a particular type of network that's able to process a sequence of vectors, and it's defined in terms of a recurrence for each time step of the sequence. So a recurrence is just an equation which defines the current value in terms of the previous value in the sequence. So we've written here the hidden state, which is h, at time t minus 1, so at the previous time step, along with some input vector for time t, that's xt, together they're passed to this neural network function f theta, where theta are our learnable parameters, and that learnable function outputs the new state at time t, so the hidden state at that point. Now, this model turns out to be really powerful. You can use it for lots of different purposes, and it can be trained in exactly the same way as we've been training conventional feed-forward neural networks so far. So let's just take a look at the computational graph for unrolling this sort of recurrence. So at the beginning, we have our first input, x1, and we need to define our initial hidden state. Usually this would just be set to all zeros, but you do also have the option of just making that a learnable parameter. So these two things are passed to our neural network learnable function, f theta, and that function outputs the next hidden state, so the hidden state at time 1. And we can continue. So this is then used as the previous state for the next call to this neural network function, along with the second input x2, and this outputs the next hidden state, and so on. And we can keep doing this for an arbitrary length sequence, and we'll call that capital T for the final time step. Now, the crucial thing here is all of these f thetas are the same function, so there's the same neural network with the same weight, and that's shared across all time steps. So we can use this structure in many different ways to solve many different problems. So let's see a few of those. So we can use it to solve many-to-many problems, for example. So in many-to-many problems, we have a sequence as input. So here I've shown x1 to x4, and we would like to estimate the corresponding output for each of those inputs. So we'll have the same number of outputs as we have inputs. So to do that, we need an extra part to our function to map from the current hidden state, h1, to the output we desire at that time step. So often this would just be a linear operation to transform the hidden state into the output. Now, if we're training a network like this, we're going to have labels for each of these outputs, and the total loss will be the sum of the losses for each of these outputs, and then the backpropagation will work as normal, but what it will mean is for the last output, the backpropagation can directly propagate into the final hidden state and into those learnable weights that predicted the last output. But then as we backprop through this chain, we're going to be accumulating gradients over the parameters inside f for every time step until we reach the initial state. So another problem we could solve would be many to one. So here we have a series of inputs, say x1 to x4, or however many up to xt. And the idea is that the final hidden state, this ht, depends on the entire input sequence. So it encapsulates all the information that the network needs in order to output its final decision or classification or whatever it is about the sequence as a whole. So finally, at the very end, this ht is transformed to our output, and we would compute a loss here and then have to backpropagate it right through this chain. We can also use a recurrent network for one-to-many. So in this case, only the first call to the neural network takes an input, and then from that we want to effectively decode across time steps, outputting multiple outputs, usually until one of the outputs indicates that that's the end of the sequence. So a good example here might be image captioning, where the input would be the image and the output would be a series of words or tokens that describe the contents of the image until we reach the end of the sentence. Okay, and a final example of how we can use recurrent neural networks is quite an interesting structure which combines two things, many-to-one and one-to-many. And we can use this for sequence-to-sequence tasks where the sequences have different lengths. So what we do is we first encode, so using a many-to-one. So we have arbitrary length input sequence, here shown x1 to x3, and at the end of this input sequence, we're going to have a hidden state ht, which completely describes this input sequence. We're then going to use a second recurrent neural network, so this is the decoder, that takes ht as its initial hidden state and then starts outputting for each time step of this decoder until we reach some signal that we've reached the end of the sequence. And importantly here, we would use different weights for the encoder and the decoder because they're performing different tasks. So a really good example here of what you might use this sort of structure for would be language translation. So this might be words in an English sentence and the output is words in a French sentence. And we can only start the translation once we've seen the whole input sentence so that we can understand the meaning of the whole thing. And of course, the two sequences might have different lengths. So we can think of training a recurrent neural network as a bit like backpropagation through time. So here we've shown some generic recurrent neural network, inputs along the bottom, hidden states in the middle in green, and outputs in blue. So each of those outputs is going to be supervised according to some label, and that will contribute to some overall loss. So we can make our forward pass, start with the initial hidden state, which is not shown here, and then work our way through passing in the inputs, computing the outputs, and computing the loss. We then make a backwards pass, so starting at the loss and following all of these different chains back through this recurrent neural network, and remembering that the weights are shared across all of these instances of the same network. So the gradients are telling us how do we change the parameters in order to reduce the loss across all of these outputs. Now the problem with this is that we need to store tensors for the forward pass as data flows through the network, and then gradients for the backwards pass. And we would have to hold this entire thing in memory in order to be able to make a gradient descent step. This adds up to an enormous amount of memory. So what we do instead is a truncated version of this backpropagation through time. So we take some sub-sample of the overall sequence and we make a forward pass, compute the loss, and then make a backwards pass to update the parameters. But we remember this final hidden state, which can now serve as the correct input for the next subsequence. So the forward pass in this case is correct. We're passing forward the correct hidden state as if we'd done this all in one go, but we're only backpropping for some smaller number of steps that we can actually fit in memory. So we keep doing that until we reach the end of the sequence, or maybe we're happy that we've trained for long enough and then we stop. But the key thing is that the gradients coming back from the loss will only ever flow to the beginning of the subsequence. So the takeaway from this is that the forward pass will be exact for any length of sequence. We can just keep going and going and we won't run out of memory. But it does mean that, for example, the weights at this node here can't benefit from the information that comes after it because we've effectively stopped the gradient from flowing backwards here. So it's helpful to see a minimal implementation of a recurrent network. So this is perhaps the simplest recurrent network you could imagine. So here's what it does. In the forward pass, it takes input at time t, that's x, and it takes the previous hidden state, and it uses that to compute the next hidden state. To do that, we just take an embedding of the current input. So this allows us, by using an embedding, we can input, for example, text tokens. And that's added to a linear layer applied to the previous hidden state. So together, the input and the previous hidden state combine to compute the next hidden state. This is a network that also outputs at every time step. So we have another linear layer that turns the current hidden state into an output for this time step. Note that the hidden states are passed through this tanh activation function. This just makes sure that the hidden state stays in range, so it'll be between -1 and 1, and that means that we can't get exploding or vanishing gradients. So just to show this mathematically, so the model here is that the new hidden state is tanh applied to effectively a linear layer here applied to the old hidden state. So these are the weights and biases, and then also added on is weights multiplied by this input token. So these are the embedding weights. And then the output for time t is again just a linear function applied to the current hidden state. So we can use this very, very simple model, just a few lines of PyTorch, to actually create a character level language model. So the idea is that the inputs are one-hot vectors representing characters of our language. And the outputs are probabilities over the different characters in our language, or at least here we're showing the logits that would then be turned into probabilities. So you can imagine the way that we can supervise this is by asking it to predict the next character in a sequence. So the input sequence here is going to spell hello, but at the point where it's only seen H, we would like the network to already predict E as the output for that time step. So we'll supervise the first output using the second input, and so on. Once it's seen H and E, that's encapsulated in the hidden state here. Then at that point, we would like it to output L, which we know is the next sequence in our input. So we'll supervise it here to produce L. So once we've trained a model like this, we can use it for what's called autoregressive generation. So what this means is we take our trained now recurrent neural network function f, we input the initial hidden state and our first input. In this case, it's the token h, so we've chosen that as our first input. That gives us a new hidden state, and we can decode that to an output. Now, what the output will represent is probabilities over our set of tokens. So in this case, it's just 4 different characters. And you can see we could either pick the most likely, so we could just take E because it's got the highest probability, or we can sample from this distribution, meaning we're most likely to pick E, but we'll pick O some of the time, and we'll pick H and L some of the time as well. So we sample from that distribution. In this case, we've picked an E, but it doesn't necessarily have to be like that. So the next version of the function sees the previous hidden state and the next character, E. This goes into the neural network function and predicts the next hidden state. Again, we can decode that to a probability distribution over the characters. From that, we can sample. Let's say we sample L this time, and we can keep going. Each time getting a different probability distribution at the output. And that comes from the hidden state that understands all the characters that have come so far. So this incredibly simple model and this strategy for sampling from the model is actually really powerful, and it's capable of learning quite impressive language models, even though it's done at the level of character tokens.